with the actual talk. So today we start our expert series, and the first speaker of the series is Professor Ivo Sachs from LMU Munich. Ivo Sachs did his PhD at the ETH Zurich in 1994, and afterwards he held research positions in different places, among them the Dublin Institute for Advanced Studies, the University of Durham, and the Trinity College Dublin. Since 2003, he is Professor for Theoretical Physics at LMU Munich. His main achievements are in the fields of quantum field theory, the structure of black holes, and the topic he will talk about today, namely string field theory. So without further ado, I hand over to our speaker, Ivo Sachs. It's really a great pleasure to have you here today.
Thank you very much. So let me share the screen. Oh, you have to let me share the screen.
I think, Linda, you have to do that.
Nope. No, it should work. There we go. Can you see this white screen with nothing on it?
Yeah, we can see it.
Okay, so that's good. Then I'll start. So thank you very much for the invitation. Then let me start right away. So as you've already said, Tobias, I will talk about string field theory, which is like the quick title. And so the idea is I will first motivate a little bit. So let me write a plan. So the plan is I will first give some motivation. Let's maybe point one, motivation. Then why one would do string field theory, or why would do string theory first of all, actually. So perhaps let me say motivation for string theory first. And then second, I will describe the construction of string field theory. That will be the main part of string field theory. And then finally, if we have time, we can perhaps talk about a little bit about applications. Yeah, let me tell you right away, string field theory is something like I like to compare to antibiotics. It's something that one should use as little as possible, but as much as necessary. And it's pretty much appropriate, I think, because it's not a very convenient tool, I would say. It's quite messy in some places, but sometimes you have no choice. Sometimes you do need to use it, and then it's good, it's there. So that's sort of the idea. Maybe it will be different in some time, that we will have a formulation of string field theory which is beautiful in its own, and then we can do it just for the fun of enjoying it, but we'll see. But so let me start with the motivation. And so what we do is we just take something. I'm assuming no prior knowledge of string theory here, so I'll try to introduce everything from scratch. And perhaps the motivation I'll take, let us consider a scattering of two scalar particles. So we have, say, two, let me take them to be massless for simplicity, it doesn't need to be. And so then, but they interact. They interact through gravity. So they're not charged, but they would nevertheless interact through gravity. So let's put maybe some momenta, K1, K2, K3, K4. And then we could compute just the perturbative amplitude. Now there is Newton's coupling will be involved, of course, and what we'll find is that this amplitude is proportional to G Newton, of course. And then the Mandelstam variables, if we take this particular one, since this looks like a T channel, SU over T. So SU, so remember S is something like, what is it? It depends on the signature, but let's take the signature where it's K1 plus K2 squared. And similarly for U and T, so just the Mandelstam variables. Now the thing is, if you suppose now you take the center of mass energy S to be very, very big compared to the Planck scale, then you will find that this amplitude grows. So this is a nothing loop quantum gravity, nothing loops. It's just 3-level gravity. So one will find that this amplitude grows, and in fact grows without bounds, simply because S will be large. So so in fact, if we take, suppose we could say that this is even approximately equal to G maybe s squared. If we take t and u, so suppose that t is order, say, smaller one, much smaller one, and then u is also much smaller one, and so then we go some approximately goes like this. And so it grows without bound. So let's write this unbounded. So now suppose you want to solve that problem. So we have a perturbative non-unitarity. So it's perturbative non-unitarity. And then you want to do something about it, perhaps. I mean, and so, but this is not something we've never seen. And so even in historical, is well known that this can happen. For instance, if you take the 4 Fermi theory, so let's just say CF, the 4 Fermi theory, before the introduction of Higgs, which is a contact interaction of 4 fermions, and the coupling constant is then the Fermi coupling. That also is non-unitary. That also grows too fast to be perturbatively unitary. And that problem can be solved. Yeah, that problem, one way of solving this problem is, so it's also non-unitary. So non-unitary, but it can be solved by introducing the Higgs particle. So if you introduce the Higgs as an intermediate internal particle, since the propagator goes like this Higgs propagator goes like 1 over p squared, that gives an extra suppression at large energies. So that's one way of resolving. So one way of resolving some perturbative non-unitarities might just tell you that you've forgotten a particle that's actually there. Of course, at very low energy, you might not see it because it's too massive. So it could be m Higgs. So you might be well approximated by just this contact interaction, but that at high energy will at some point start resolving this contact interaction, and then you'll find that's one way of unitarizing such contact interaction. Let me see, are there any questions here already or comments? So just please ask at any time, just interrupt if there's anything that's not clear or maybe wrong, it's also possible. So now, let's suppose we want to solve this problem. We will discuss in a little bit whether we actually do want to solve this problem, but let us for the moment assume that we want to solve this problem. So then we might follow the same route. So we might say we have here a particle, which is the graviton, which has a spin 2. We'll put J equal 2. And suppose we want to add another particle to resolve this. So hoping that maybe if we add spin 2 we already used, but perhaps we could add a spin 3 particle and higher spin also. We could try. And then we could hope that perhaps if we do that with suitable couplings and fine-tuning things nicely, that actually this thing will work out as a bounded amplitude, just like it worked for the Higgs. So one could try to do that, but it turns out that it's not so easy, actually. So if you try to do that, what you will find, so suppose you insist on perturbative unitarity, then what one will find is that if you want to include one particle of spin bigger than 1, so say the graviton, for instance, then if you want perturbative unitarity, that will imply that it's actually not enough to introduce a few more higher spin particles, but you need an infinite number of those. So you need J needs to actually be 1, 2, up to infinity. So you actually need an infinite number of particles with increasing spin. Otherwise, at some point, I'm not going into details here, but you just look at the partial wave decomposition of this amplitude, and you'll find that this otherwise is not possible. But not only that, you will also find that these higher spin particles will actually have to have a mass. That's denoted by mj is the mass. And the mass of all these different higher spin particles cannot all be equal. Actually, also has to increase with the spin. So, and then even that turns out not to be enough. So on top of it, you will also need to have at each spin, for each J, you need an infinite degeneracy. In the spectrum. So you need infinitely many particles with a given spin. So it's not guaranteed that if you do this, so you add to this amplitude which you already had, all these terms, it's not guaranteed on its own that this will give you a unitary theory, but you can show that perturbatively, if you want it to be perturbative, you need this. Now, that already turns out brings you pretty close to string theory. It doesn't tell you that these masses have to be equally spaced, that you go from spin 2 to spin 3 to spin 4, that you always have to increase the mass by the same amount. But it turns out it has to increase, but this you don't show. In string theory, that is the case. So now, okay, so that is just a mathematical fact. And so you want perturbative, suppose you want this particular perturbative amplitude to be unitary, then perturbatively unitary, then you will need all these fields. Now, of course, you put in certain assumptions, you assume local interactions, you assume the usual sort of assumptions of perturbative quantum field, local perturbative quantum field theory. So now then you may ask, suppose there is this situation, can you compute the amplitude for if you have so many spins? Might be hard. You might say, okay, this is going to be a very hard problem. You have to so many particles, you have to add up all these diagrams. That might be very hard. And indeed, generally, it would be very hard, but turned out there is a perturbative solution which was found a long time ago, sort of by, I'm not sure, I wouldn't say by accident, but it's sort of by perhaps a little bit surprising, which was called the Virasoro amplitude, and that was in 69, I believe, 1969. And I'll tell you what it looks like. It looks like this. So the amplitude, which is a function of the Mandelstam variables A, S, T, and U, is going to be something like this. So G squared is the coupling constant, and then you have these gamma functions. You have gamma -1, and then minus alpha prime is a constant times S, so the first Mandelstam variable, -1 minus alpha prime T, gamma -1 minus alpha prime U, we haven't used, it's many, divided by gamma of 2 plus alpha prime S, gamma of 2 plus alpha prime T, gamma of 2 plus alpha prime U, I guess. And remember, in the physical regime, you have in S is bigger than 0 and T and U are smaller than 0. That's when you are in the physical regime for the scatter. So that amplitude was given, and you can look at it, and it has all these nice properties. It looks like, actually, if you try to factorize this amplitude, you'll find that indeed it has poles, say, for infinite, it has poles at infinite values of the mass. So and also you can work out the spin of this resonance or of this intermediate particle, which would contribute to such an amplitude. And you'll find it has all these properties. It's indeed an amplitude which involves interior particles with infinite number of spins and infinite number of masses, actually equally spaced in this case. So I should say also alpha prime is a constant. So alpha prime is a dimensionful constant, which has a dimension of length squared. And it will be later be entered as the string tension, but for now it's just the constant has to be introduced for dimensional reason. So, and now this is actually, interestingly, this A of S, T, and U is not just the amplitude for the T channel amplitude. I'll go up here again quickly. Here we have the T channel. I just draw it. I just did draw the T channel, but actually sums over T, S, and U channel. So this is really includes, so that amplitude would be something like this, plus also this, plus also, which one is the other one? So you have this maybe, this. So that would be then S, T, and U channel. So it's the sum of all. Okay, so this is what is, even at that point, you're just thinking of trying to produce an amplitude which has all this which does actually involve infinite number of particles. And it turns out it has a nice high energy behavior. It falls off exponentially in S for large S in the physical regime. So it has all these properties. So apparently such an amplitude exists. Now, of course, then you might ask, where does it come from? Yeah. Does it come from anything? Is it just a mathematical formula, or is it something physical? So now that is that is resolved not much later, actually, I think more or less at the same time by Nambu, who found that indeed you can factorize this amplitude in the following way, that if you take, suppose, and that's just one representation of this amplitude, which looks like this. Now, of course, you already see the string arising, but just at the moment it's purely sketchy to parameterize something. And then we write this this amplitude given by this. And we have to, of course, say what we mean by this drawing. What we do is we put here, say k1x, here you have k2, this was, and then here is e to the ik1x. So this is just a wave function of a plane wave with momentum k1. This would be a plane wave with momentum k2. And that, of course, is not enough. What you have to do is then that would, if it was just that you had the two plane waves which are colliding, that would be perturbatively scattering two scalars. That's fine. But in fact, you have to add higher spin particles. And the one way to parameterize that is you actually introduce an auxiliary circle, which is purely here for parameterizing things, because these circles, what they can do is you can say, well, I could actually say that my x can be written as a, so let's say perhaps, yeah, x, I can write it as a function of this extra variable sigma, right? And then I write it as sum over n, perhaps some x0 plus sum over n, and let me write it perhaps as alpha n e to the I n sigma. So it's really just the oscillations of this circle. So you have here, you just do a Fourier, you can say you have a function which is defined on a circle, and you can decompose it into modes, into frequencies, or into momentum decomposition. Okay, one can do that. Suppose you do, and then you define a state by taking these plane waves, and on top of it, you act with these alpha n's, or actually I should say minus n for n bigger than 0, and maybe you have here alpha n, n1 minus n2, and so on some Fock vacuum, just like you would do in a harmonic oscillator. In a harmonic oscillator, that's exactly what we do. We take some Fock vacuum, we act with some creation operator, a dagger, so it's called n2. So n denotes the frequency of this harmonic oscillator. So if you have only one harmonic oscillator, you have only one frequency, so there's only one a and an a dagger. But of course here, as you know, for the guitar string, it has different, you can, depending on how you can excite different harmonics. So you can have, so we can have different, for each n corresponds to one frequency. So you have many harmonic oscillators. You don't have just one harmonic oscillator, but many harmonic oscillators. And then you can have, each of these harmonic oscillators can be excited once or several times. And every excitation of this, so this parameterizes.
Sorry, Ivo?
Yeah.
There was a question in the Google.
Mass. Yeah, and I'm ready. Good.
Thank you. There was a question, an anonymous question. So it is, could one take S squared instead of S1 as a parameterization? So as long as it is compact, one gets a discrete spectrum, right?
S squared, what is meant by S squared?
So S2 and S1 probably.
So instead of taking a circle, one would take a sphere, for instance. Yeah, one could try, you see, one should really look at it the other way around, but we can discuss that question. One should really look at it the other way around. The way Nambu found is just, he found that you can parameterize, or you can factorize this amplitude in terms of harmonic oscillators. Not just one, but you need infinitely many of those. So that's really the way it was found. So first you find that this amplitude can be written as, can be described in terms of harmonic oscillators. But you need infinitely many of those. And it turns out that so in order to describe these infinitely many harmonic oscillators, enough to have an S1. You could do it S2, but then you have too many, so you don't need it. So you can describe these infinitely many harmonic oscillators just with a circle. In fact, there were earlier attempts to understand this amplitude with just one harmonic oscillator, and that failed. And then Nambu found actually you need infinitely many, but you can they can be parameterized by a circle and by a string in that sense. So, okay, so that in a way was the birth of string theory. So then you say, okay, you have the string is like, you can think of the string as being like a point particle as the center of mass. But that would be if it's not excited. But you might also excite that string, just exciting it. I'm sort of drawing that like here, and you could excite it. And depending on how many wiggles you want to have, it tells you what's the frequency of the excitation, and you can excite it once, twice, or many times, like as a coherent state if you want or not. So the string is some sort of excitation of a point particle into a string. Okay, so but that is just the way it was found is simply a way to factorize this amplitude which was found previously without talking about the string. It's just an amplitude which has this property, which we needed. Okay, so hopefully that will sort itself out. Yeah, so that's good. Okay, so now, yeah, let me say a little bit more about this. So now, of course, we find there's one way to write this. Is there a convenient way to do calculations with such an object? Now, the one beautiful thing, I think, or convenient thing about the string is indeed this geometric picture. Because if you didn't have this geometric picture, it would be very hard to do all these calculations. You would have to be taking account all these oscillators here, so many of those frequencies, so many of those frequencies, you have to commute them through each other. So you'd never probably do an interesting calculation because it would be just too messy. Now, but because we can represent this in terms of just an oscillating string, we have this geometric picture. And what we can do actually is we can write this amplitude of 4 particles. What we do is, we had already said, we take this plane wave. On top of the plane wave, we excite the Fock vacuum, and we define this as some vertex operator. Some operator which depends on the momentum, in this case K2, and then also on all these N1, so on. So what you can do is you take this vertex operator, V of K1, and let me write here all the other excitations, and then V of K2, and then another one, 3, and finally the 4th, which corresponds to the 4th particle. And what you do is you think of this as a correlation, an expectation value of these 4 operators, and you have to insert these. I mean, you have to take this expectation value with a certain measure. Right? Like in statistical physics, you have to always define what is the expectation with respect to which measure. And what you can write is, you write it like this. It's simply the Gaussian measure. So you take functional integral over x. Here we insert all these operators, and then with a certain measure, we take here minus d sigma, dt, and then we take, this is with respect to sigma and t, so nabla x mu, sorry, I get it, nabla x mu with nabla x mu. And this nabla is the derivative with respect to sigma and t. So, and then x is, as I said, x, you think of it as x is this little x mu, which is just the center of mass coordinate, plus then you need some dimension for quantity in order to get the dimensions right, and then you write here sum over n, alpha n, e to the in, and then sigma minus t, and then plus, let me write alpha twiddle n, e to minus I n sigma. You just have left and right movers. So if you have an oscillation on the string, it can turn clockwise or anti-clockwise. And then these two, if you take for n negative, they will create excitations out of the Fock vacuum, and for n positive, they'll destroy them, just like in the harmonic oscillator. Now, the details of this, how this is calculated, I will not do here. Also, it's not important for us. Just what one sees here is that indeed this is actually turns out to be the tension, the tension of the spring. So the string tension. So string tension. So it's related to how long how strong the spring is, and what's the energy associated to each oscillation. Okay, all this works. So this is just the idea described above. It's just we want to have a perturbatively unitary amplitude. That's not, by the way, historically how it happened, but it's the way I would like to present it. And you would like to have a perturbatively unitary amplitude. There is such an amplitude. If you want to factorize it, you can do it with this theory. That gives you. However, we should say that what we compute here is an amplitude, and it's a very specific amplitude. Actually, all these tricks which I used here, they only work if each of the external particles are on shell. And so I have to have ki squared is equal to mi squared. So you have to be on shell. Otherwise, all these manipulations don't work. So that's one thing. And the other thing is that this amplitude which you get in this way, the one which I computed, which A, S, T, and U, which I wrote as this expectation value of these V's, turns out to be, again, it's the sum over all channels, is S plus T plus U channel. So what I'm trying to say is that you use this procedure, which works, but it gives you not the individual amplitude, it gives you just the sum over all amplitudes. So now then you may ask, where does that come from? You know, is there a field theory? Because normally that's not the way we do calculation. That's not the way how we learn to do calculation in quantum field theory. Usually the way, at least when I was young, we used to learn how to do calculation in field theory is you first write down a Lagrangian, then you read off the kinetic term, which gives you rise to a propagator. Then you read off the interaction terms, which are the polynomials in the phi, and then you build Feynman diagrams. Then you sum over all Feynman diagrams, you integrate over the momenta, and that gives you an amplitude. That's not the way it worked here. We come right with the amplitude. So this procedure goes right to the end, which is reminiscent of S-matrix theory, where you don't care too much about where does this amplitude come from. You just want to know what's the S-matrix. That was called the bootstrap or the S-matrix theory, which was popular in, I guess, the 50s, before the ascent of quantum field theory, relativistic quantum field theory, renormalizable one, and then got a little bit perhaps forgotten. And now recently, as probably you know, has become popular again with this modern way of computing amplitudes is a little bit more along these lines again, where you don't ask too much what is the Lagrangian, but you just use certain properties of what these S-matrix amplitudes have to have in order to determine as much as possible of them. That it turns out to be often a much more efficient way to actually compute them. And string theory, in a way, does that for you right away. String theory is built in such a way that it does exactly that. Nevertheless, some questions might not be answered in that way, because suppose you know what is an S-matrix. Suppose you know the S-matrix element. What can you guess from it? Well, you know, of course, you can compute cross sections. You can ask what are decay rates. You might find some resonances. You look at poles. You can find widths. So you can find the lifetimes of resonances. But what you will perhaps not find is, for instance, a black hole solution. Because it's always perturbative. By nature, it's a perturbative approach, which will tell you how infinitesimal fluctuations around a certain background, how they interact. And they might say, oh, they create some resonance, and then you get a pole, but you will not find new backgrounds. That in S-matrix is not the information that's contained. So it has a lot of information about perturbative physics, but it doesn't have too much information about non-perturbative physics. And that's why one would like to have perhaps to know what is the Lagrangian or the action that gave these amplitudes after you do the usual procedure of Feynman diagrams and so on. So that is what that's the purpose of string field theory. String field theory is precisely trying to reconstruct an action which leads to these amplitudes. I see a look in the chat. There might be a question.
No, I think there are at the moment no questions on the chat.
Very good. So, but we can still see if there are any right now. Okay, maybe for completeness, I should say, before I go on, that one might take a different route. One might say, perhaps theories involving gravitational degrees of freedom are not perturbatively unitary, but they're nevertheless non-perturbatively unitary. And then that's also okay. That just means perturbation theory breaks down. So that would be another approach, which I will not follow here, but let me just mention, sometimes this gets forgotten, that especially in the string theory community, that one could also consider, or maybe CF, non-perturbative unitarization. And so one way, for instance, I could say, okay, we have considered this scattering of two scalars, and suppose now, say that not in the regime where we were just now, but suppose we are in the regime where T is very large, much bigger than the Planck mass. Then you might say, okay, there's the one graviton exchange, but you might also exchange many gravitons, and you should sum them all up, and maybe each diagram itself will look like it's unbounded, but if you sum them up, it will actually be bounded. And so that is sort of what's underlying the idea that once you scatter particles with very large momentum transfer, you actually create some classical configuration, or something which looks a little bit like a classical configuration, which regulates the integer. So these are ideas that have been followed by many people, also more recently by Twali, for instance, Gomez. And there you say you have maybe something that looks a little bit like a black hole intermediate state that then actually has the right property to unitarize this theory. So that's a non-perturbative proposal for a non-perturbative unitarization. That's one possibility. Another possibility, you might also say, well, even the whole question makes no sense. In the following, this I can explain, is suppose now again you have a very energetic scalar particle, for simplicity, and you have another very energetic scalar particle. Now, we know that gravity couples to energy. So you have a very energetic scalar particle. It will necessarily deform space-time simply because the energy couples to gravity. So one way to do that is to picture that is that you somehow, this very energetic particle doesn't actually exist as an asymptotic state, but it's always stressed with a huge number of gravitons, offshore gravitons, not spin. And so would the other be, this one also. So there is no such thing. Remember, you know this thing very well. In fact, even in QED, there is this question: is there such a thing as an asymptotic state? I mean, asymptotic state is a state which is non-interacting. Now that depends. If such a concept is well defined, it depends on how quickly the interactions fall off. And we know that in QCD, for instance, this is not a problem because at very large energies, the QCD interaction, the strong interaction are very small, so they fall off. So you can have a very high energy, makes sense to talk about the gluon. In QED is a little bit tricky, but seems it works. In gravity, one actually say almost certainly doesn't work, right? Because if you have a very energetic particle, necessarily it will create gravitons, offshore gravitons, and therefore such a concept doesn't really exist. Although then you might say, well, I can solve this problem. I just do a Lorentz boost in such a way that the particle that went very fast is now at rest in the new frame. So problem is solved. Now it doesn't have very high energy. Now then you might do that. So that would allow you to remove these gravitons because this one is now almost at rest. But of course, by doing so, you make this one all the faster. And then the other one gets even more interacting. So really, in some sense, this notion of an asymptotic state with large energy is not really well defined when you have gravity involved. So then you might say this whole question of having a perturbatively unitary theory at trans-Planckian scale is actually not really well defined. I think that is probably a fair statement. So anyway, but suppose you might then say, okay, once knowing that, you might say, okay, then maybe one can find a better way to describe it. And indeed, there are Ansätze where you say, okay, let me take into account this back reaction. And there are certainly cases where you can take it into account. This goes to back to work by de Hooft, I think in the 70s, Veneziano, where you have shock waves. So you take, these are very special configurations where you have a shock wave, which is precisely that, a very energetic particle which deforms space-time, and then the second particle scatters in this background. You could also do that by replacing the first particle by a very energetic graviton. Suppose you take a very energetic graviton, which will also backreact, and will create something under suitable conditions, which is called a PP wave, a plane-fronted wave. So this is a fully backreacted solution, nonlinear solution of Einstein equation, which at very small energies would reduce to a graviton. And then you can say, suppose you have a second particle which scatters in this background. And it will, of course, exchange some graviton. But the fact that it exchanges not just one graviton, but all the time, actually turns out to unitarize to some extent this, this amplitude. So that is something you can calculate. And indeed, you can find for some very specific scenarios. There was something done with Tung Tran, who was a student, that you can actually unitarize this perturbative non-unitarity becomes bounded. So this is, I'm not going to follow this route here at all, because I'm going to talk about string field theory, but I just wanted to, it's always good to also ask, am I actually trying to solve a problem, or am I trying to solve a hypothetical problem? And I would define string theory as it's more or less pretty much unique, not perhaps fully unique, but pretty much unique theory we know of perturbatively unitary theory involving gravity, where you can do actually calculations, where we can start with a where we start with four gravitons, and then you just do order by order perturbation theory, and you want to see that it all makes sense. So, but as I said, this may not be necessarily the problem that nature has chosen. It's always good to be. Anyway, so coming back to this. So now we defined what string theory is, and the question was, what is string field theory? And as I said already, string field theory is just a way to find a Lagrangian, an action, a space-time action, which gives rise to this amplitude, giving rise to ASTU. All right. So let me perhaps give you first what will be the result. So it is possible. It is, so that the answer is it is possible. So it can be constructed. Perturbatively. What this means is that you take a certain background and you build a perturbative action around that background. That's like, you know, take a phi-4 theory and you choose a certain value for phi, background value, and you expand around that value. You assume the deviation of the field is not too far from that background. In that approximation, string field theory can be constructed. It's not entirely satisfactory because it's not background independent. You choose a background and then construct it. Then you might choose another background, construct a new. It's not easy how to compare the two. So, but that is the state of the affairs. Another result is that this action, let's say space-time action S, the action you find S is based on a non-associative or perhaps non-Lie, depending on what sort of whether you do open or closed string algebra. What this means is that normally in field theory we can multiply fields with each other. Phi-4 theory is phi times phi times phi. And it doesn't matter whether first you multiply the first two phi's and then you multiply the third or the other way around. In string theory matters. So it's just the way it is. So it seems like that's something you buy. Then the action is non-local. in a very specific way. Let's say in a very specific way, which I will hopefully describe a little bit. And the third thing, which is more of a technical observation, S is naturally formulated as a BV action. So what's called a BV is the Batalin-Vilkovisky. Some of you may know the Batalin-Vilkovisky formulation. Some of you may not. Doesn't really matter. The thing is, actually, when you do string field theory, you don't need to know what this BV formulation. You just find it in a way that is not usually the way it's derived. And usually, when you do a BV action, means that you take a gauge theory with a gauge redundancy. You gauge fix the theory using the BRSD approach, and then you find that there would have been another way that you could have actually done the whole BRSD approach even before gauge fixing. You sort of, rather than introducing BRSD charges and BRSD ghosts, you could say, I do this from the very beginning and gauge fix later. If you do this at the very beginning, you introduce already all the degrees that the BRSD formulation induces. You will find the BV action. In string theory, just there's no way around it, basically. If you do covariant string theory, you just fall on it. But that is more a technical. I'm not sure to what extent this is conceptual. I'm not entirely sure. Okay, so what I would like to do in the following, I would just like to describe a little bit this construction, and then we will see a little bit how these points come about in the construction. But let me see first if there are any comments, questions.
Maybe just regarding the time. So actually, there are, I think, from the plan only 6 minutes left now. I don't know.
That's even that is okay. Don't worry.
But okay, but we can maybe have 10 minutes longer due to this stuff in the beginning. So
all right.
Yeah.
Okay. Good. All right. So let me see here. Okay. Unfortunately, this program seems to now. Okay. So what I'm going to do in order to describe the construction, I'm going to take a simplifying assumption, which turns out to be not a good approximation, but it explains pretty much everything that you need. I'm going to take the limit where alpha prime goes to infinity. That means the string tension becomes huge. That means all the massive excitations become very massive, so they go just away. They're not excited. So what you end up with is a point particle. So in that case, this measure which we had, which was this nabla x mu, nabla x mu, will just reduce to a relativistic point particle. So d tau, and then you write E over E x dot mu x dot mu. So all the excitations on the circle have become too massive to be excited. So x dot mu is just d by d tau of x mu. So it's the proper time. E is what's usually called an Einbein. It's just guarantees for the reparameterization invariance. This combination here, actually, this combination is invariant on the reparameterization of the word line. In the relativistic particle, this is something natural to do. Do not fix this. Okay, so now actually turns out that's one way to present this word line action, but there's another way which is a bit more convenient in that case, is you use the Hamiltonian formulation. You write as p mu x dot mu minus E over 2 times the Hamiltonian, which in this case is just p mu, and then d tau. So as I said, this is reparameterization invariant. I can reparameterize it, provided I transform, just like in gravity, just if I transform the metric of the word line. Okay. And then, since you have reparameterization invariance, this is a, you can vary with respect to E and you get a constraint. And the constraint in this case is just the Hamiltonian constraint, it's H. And you have to impose, so H is equal 0. What we mean by H is equal 0, it's weakly 0. That means H acting more precisely H acting on any physical state has to be 0. Now, if you, now if you translate that, that means p squared psi, or in terms of wave functions, is that Batalin on phi is equal to 0, which is just the Klein-Gordon equation. So the reparameterization invariance of the word line implies in space-time, once you represent this reparameterization constraint, the Klein-Gordon equation. Fine. You can expand this a little bit. Okay, let's maybe not do it in view of time. But what we can do is we could now BRST quantize this point particle. Because we had a gauge freedom, we want to fix it. We fix BRST quantization. Fix E identically equal to 1. But by doing so, it's better to introduce ghosts, which take care of the extra gauge symmetry. So what happens is your word line action becomes actually PQ dot, PX dot, sorry, not PQ dot, PX dot minus a half P squared, which is the Hamiltonian, and then you get also a P, the usual BRST ghost, B ghost and C ghost. So the reparameterization is replaced by a C ghost. So now you can define a BRST charge, Q BRST, which you define as C times this Hamiltonian. Now, this is the word line BRST operator. You have to represent it on wave functions, and that we have already done it. It gave you this. Now, you can say that this is, of course, a nilpotent operator simply because C squares to 0. That implies that Q squared is equal to 0, which is fine. That's usually what we expect for a BRST operator. And you can also write down a space-time action. And the space-time action you write down is you can sort of guess it by simply saying, well, I know the Klein-Gordon action, so let me write down something that looks similar to the Klein-Gordon action, which is phi. I simply write it as integral d4x phi. But now I want to use this BRST operator, so I can write here a q, and I write another phi. But then you have the problem, the q involves the C ghost, whereas the action should be a number, so what you do is you integrate also over dc. So now this is a one way, and then if you work it out, this is just integral over space-time phi box phi, which is the Klein-Gordon action, nothing special. Okay, so there we go. Now this thing turns out defines a symplectic form. So simply because of this is an odd symplectic form, you can write this as phi q phi. And because of the C integral is an odd form. So that is the kinetic term for, so to say, the string field theory action for this relativistic point particle. It's a little bit boring, of course, because it's just Klein-Gordon. You could also say, maybe I would like to add interactions. So I would perhaps like to have something like phi cubed and so on interactions. You could say, okay, let's do that. What we do is we replace this and we add omega phi and then phi star phi. What is phi star phi? Well, I just have to get this. So what you find is, because you have this dc integral, you need to put a c somewhere here so you can integrate over c. So simply you define this as being the normal product phi squared, but multiplied with a c. Now you have one c, you integrate over c, c is gone, and then you get a phi cubed. This is by hand, and this is constructed. There's nothing that tells you have to do it that way. That was purely pedagogical purpose. Now, since, as Tobias said, we have to rush a little bit on time. So what I'll do is I'll just tell you how the same thing happens in the string. The only difference in the string is that, oh, let me say one more thing before I go to the string, is that we have now two objects. We have the BRST operator, and we have this star product, which is really just the normal product multiplied with a C ghost. They form a differential graded algebra. Differential is here because it's a q squares to 0, so it's a differential. The star gives you multiplication, so it's an algebra. It's graded because of the C ghost, and you have certain properties. You have q squared is equal to 0, and q commutes with the star product. It's, if you check it, it's trivially, there's nothing, you know, it's a one line and it's really not hard to check. String field theory is the same. It's no different, just with many more degrees of freedom. So in string field theory, the only thing that happens is that because we have to now blow up our particle again, phi is no longer just a function of x, but it's a function of capital X, which is really itself a function of the string coordinate. And on top of it, we also have the ghost, which is not just an odd variable, but it itself depends on the coordinate on the circle, similar for the B ghost. And then you can decompose this again in sum over n, bn, e to the I, n, sigma plus t, and so on, just like we did before. So the idea then is a state phi is simply, let me write it like this. You take like a disk, and on the boundary of the disk, you can say what is the probability, or what is the overlap of this function. So you have a state. Okay, sorry, didn't say that well. Let me repeat it again. So what we can do is we can take a state phi, which corresponds to a certain operator inserted here. Remember, we inserted these operators. That gave us the initial particle. And then this will give rise to a, you propagate this in this way, and this gives rise to field configuration here as a function of sigma. So this is the sigma variable, goes in this way. And then you can define an inner product simply by saying you take this phi, sorry, write it here. You take this phi, you take phi of sigma. So this is one which has a definite dependence on sigma. Let's see here. Try it again. So I integrate, let me make it like psi, another psi, and then phi. And what I mean by this integral is integral over all phi of sigma. And then you test this state with a wave function phi of sigma. So I should write to phi, and then psi phi. So these are fixed sigma dependence. That's like the X basis in quantum mechanics. So you have an inner product, and you can also insert the BRST operator here if you want. Sorry, BRST here, if you like. So then I would have to do it here. So I can define an omega of psi q psi, just in the same way as I would have done for the point particle above, just that now everything has infinite number of field content, because you can decompose every field into Fourier modes in the sigma direction. Other than that, you just repeat. And now maybe, I'm not sure how much time Tobias will give me.
Yeah, I think 5 minutes.
5 minutes is good.
So 5 minutes.
So the only question now that one has, so we have already guessed what would be the kinetic term of string field theory. So it's this. And so all we've done is just taken the point particle and we added each frequency. We did the point particle for each frequency separately. This is diagonal in this basis. But what are the interactions? Now, in order to guess what the interactions were, we have to do the following thing. We say, well, we knew in string theory, we know we can compute S matrix elements by simply computing this correlation function, remember, on this thing. Now, what I can do is I can try to decompose this into pans, tubes, and pans. Right, like this. And then I'll say, so this is my vertex. This is my another vertex. This is a propagator. I can decompose every worldsheet with 4 punctures in this way. Actually, turns out you cannot quite. Because one thing we have to do is we have to put a state here. So purely on the geometrical side, you can decompose every sphere. This is topological sphere with 4 punctures. You can always decompose it into a sphere with 3 punctures, a tube, and another sphere with 3 punctures. That is always possible. There's no obstruction. However, here we need a little bit more. actually, let me still write that equation first. There is an equation which describes precisely that, is you say this is a vertex, a geometric vertex, nu 3, because it has 3 punctures. This is a nu 3, has 3 punctures. And there's one way of saying that if you, more generally, you take a d nu with n punctures plus, what do you write like this? P, Q, P plus Q equal n plus 2 equal to 0. What this tells you is, there we are. What this tells you is that you take every vertex with n punctures can be decomposed. Oh, actually, if you have a vertex with n punctures, if you have a sphere with n punctures, you can always decompose this in propagators plus vertices. And what this d here does is it just shrinks the propagator to 0. So basically what this equation is telling you the following thing. If you have the S channel amplitude and you have the T channel amplitude, and now you can make this length to 0 and you can make this length to 0, that they should meet. Right? That this diagram, which you get when you make this length to 0, and the diagram which you get when you let this length go to 0, that they are actually the same, that they meet in the middle. So this is the content of this equation. And this just tells you that there is a consistent decomposition of the moduli space of spheres with n punctures into pans and tubes. And that actually is always possible. This is what's called the geometric PV equation. Let me now tell you why. But this is just the way, that's a purely geometrical object. Now for us, it's not quite enough because one has to do the following thing. We have to put little physical states because so far it's all geometry. We have to put here states. The way we put a state, we look up here. We've learned how to do it. Here it is. There's a state. So I have to take this state. I have to glue it onto these little pans. This gluing you have to do with some nice mathematical mapping that maps this disk to here. But in order to do that, you have to define coordinates. So near every puncture, you have to define a coordinate in order to glue these disks to these pans. And this is extra data, which is not geometric, is not topological. Right? In topology, you don't have coordinates, but so this is here the topological equation. But now we need this extra. And then you find, for instance, the sphere with, the sphere with 4 punctures. You can put little coordinates around each puncture, so you can glue the disks into it. And then you might ask, is it again decomposable into pans with 3 punctures and propagators? And the answer is no. It no longer works because as you vary the distance of the punctures, eventually what will happen is that the coordinate patches start overlapping. And that's not allowed. So then you need to actually add to this a 4 vertex, which is what's the leftover of the part which you could not write into pans and tubes. That is because of these coordinates. But then once you've done that, you're done. And now you just say, okay, now I know what to do because I know how to compute these vertices. I put now my little states here. The vertex operators correspond, let me put here psi1, psi2. I know how to put them there. And then I know how to compute expectation values. And then, in fact, you can construct the action, which is now omega psi cube psi, we'd already discussed this, plus 1/3 or 3 factorial omega psi L2 psi psi plus 1/4 factorial omega psi L3 psi psi psi, and it goes on. And what these L's are, this L2 is nothing but the expectation value on a 3-punctured sphere together with this. And this is the expectation on this. This gives rise to the L3 and so on. But turns out you need infinitely many of those. So string field theory will have this form, kinetic term, a cubic interaction, quartic interaction, quintic interaction, and actually because of this problem of the overlapping coordinate patches, infinitely many. So it's a non-polynomial theory. It's the way it is, nothing you can do. But furthermore, you will find that it's not true that the L2 composed with L2 of, say, A, B, C is not equal to the same. So, okay, let me write it concretely. What I mean by this is L2 of AB with C is, and then plus L2 of A, L2 to B, C. That actually is not equal to 0, but this is equal to Q, which is this Q here, of L3 of A, B, C. And this is precisely the defining equation for a non-associative algebra. So you have non-associativity. These two things don't give the same result. That's just what comes out, is life. So there you see that this theory is apparently non-associative, because these vertices, which you get by doing this, this decomposition, is just the way it is. Finally, because I promised, I want to tell you why it's non-local. It's non-local simply because of this mapping. You have to take this state, which was defined on a disk, or a unit disk. You have to map it, glue it in here. Gluing it in here needs a mapping. What in geometry is called conformal mapping. You just map this disk to here. And this mapping will stretch, or will typically stretch a little bit, this disk. And then as a result, this translates into, so L3 will be of the, let's say L2 even, of AB will...
Sorry, Ivo, I think we have to wrap it up maybe in a minute or so.
Yeah, that's fine,
okay,
because I'm
great.
almost done. So then this will be something like A, and then you get a small value T with some D'Alembertian acting on B, something like this. And here you see the non-locality. So this is the type of non-locality, simply comes from stretching this disk. So all this is geometric. And I think here I should really stop, and let me stop so we can summarize. So maybe let me go back to what I promised, and I hope I explained all the things which I promised. Let me agree. So it can be constructed perturbatively. It's non-associative. It's simply to do with the fact that these vertices which you get from this 4-punctured sphere and 5-punctured sphere and so on, that they don't have this associative property. It's non-local. And I didn't really get to explain why it's a BV action, but you can always ask me about it in the questions if you like. So then maybe is a good place to stop. Thank you. Okay, yeah, thanks a lot for this very nice talk. We have now still 45 minutes for questions, and maybe